This is the second lecture over quadratic functions for Math 107, Chapter 2. In the previous lecture, I pointed out the important points on the parabola that need to be determined for a quadratic function. Those points were let's say this is your parabola coming through like this. Pretty bad parabola, but there you go. Okay, you need to find the vertex, which is your H and K. So this vertex, we either have to solve for it, or if we have the graphing friendly form, we can just read it off. The other thing we need to determine is whether the parabola opens up or down, and that has to do with just looking at the sign of the coefficient of the x squared term in either equation. Right. Then the other points we need to find are these x-axis intercepts, these roots. So there's two of them. Okay. Now I'm going to write first the regular form for the quadratic function. It looks like this. Now, why are there two roots? Well, in general, when you have a polynomial like this, the highest coefficient of x, of the independent variable, in that case it's 2, tells you how many roots there are. There has to be two solutions for each value of y. If I want to find the two solutions where the parabola crosses the x-axis, at that point y is 0. So I have an equation like this, y ax squared plus bx plus c, and I'm looking for two solutions. Okay, now I'm going to talk about several things that seem to happen in threes. How do I solve an equation like this? Well, there are three ways to solve the equation. The first way is by factoring. If it's easy to do, don't do it if it's difficult. If you can immediately recognize the factoring, then you can factor it. Set each factor to 0, and you will get your roots. The other way, which is a little more complicated, but some people will like it, and it's used for other things when you get into trig. That's complete the square. Right? That's the second way. And the third way is a quadratic formula. Quadratic formula gives us more than the solution. It gives us insight into quite a few aspects of this parabola. So this is your quadratic solution. All right. So you just go and grab the quadratic solution and use it. You're probably familiar with that. By the way, you never have to memorize a quadratic function in this class. It will be written on the top in the reference section on the test. That doesn't mean you're going to use it correctly. So you need to familiarize yourself with the quadratic solution. You can't just or people grab it and do weird things with it, change signs, all kinds of stuff. So you need to practice with it first, even though it's there and you don't have to memorize it. So now I want to talk about something else that occurs in threes, and that's the kind of roots you get. It's easiest to see this if you look at the graph. So I'm going to draw three graphs of parabolas. This will be case 1, here's case 2, and here's case 3. In case 1, the parabola, in this case, opens up, but it could open down as well, crosses the x-axis in two distinct places. In this case, the roots are two real distinct roots. Right. Now if you think that this parabola is moving up and up and up and up, you would see that those roots are getting closer and closer together. There is a point where the parabola comes down and just sits on the axis, just hits it in one point. In this case, you have two real equal roots. There's really two of them. They just have the same value. You might think that's kind of quibbling, but that's how it's done. There really are two roots, and they have the same value. Now, if the parabola moved up and never hit the x-axis, are there any roots? Yes. The roots are a complex conjugate pair. So you have complex roots, and they occur as complex conjugates. You don't see them, you can't draw the roots on there because they have imaginary parts, and this is a real axis, and so you can't draw this imaginary, my y-axis and x, of course, and you can't draw them on here. So graphically, the graph would look like that. You'll have the same thing if the graph is opening down. It might look like, in this case, it's opening down, but it will never hit the x-axis. This would be an example of complex conjugate roots. Here, it might come up and just hit in one spot, or you might have a graph that's opening down and hitting in two distinct spots. So those are your three types of roots. So there were three ways to solve, review. One is factoring, one is completing the square, and you do whatever's easier or whatever you're directed to do. And then the third method of solution is using a quadratic formula. Right. And then you can get three kinds of solutions: two distinct real roots, two real equal roots, or roots that are complex conjugates. Now you can see graphically what you're going to get here, but there's an algebraic way to figure out whether your roots are going to be distinct and equal real roots or complex conjugates, and that's by looking at part of the quadratic formula. So here's a quadratic formula, and this is the way I want you to write it. X equals minus b over 2a plus or minus the square root of b squared minus 4ac over 2a. Sometimes people on books write it with the like this. They go minus b plus or minus square root b squared minus 4ac all divided by 2a. Don't do it that way, and there's a reason. I'll show you that in a minute. So writing it like this, okay, I'll tell you the first reason. The first reason is, what if the roots are complex conjugates? For example, you know what complex conjugates are. Say x1 is 3 plus 7i. Then you know the other root has to be the complex conjugate, 3 minus 7i. Okay, where do you get this plus or minus sign business? Right out of here. So if you have complex conjugates, then by writing this way, you have separated out the real part. This will be the real part, and this will become the imaginary part. So that's one reason for writing it in this way. Another reason, and this is a great time saver, is to realize that this leading term here is h. So in this case, we're looking for the roots and the vertex. This is a solution, this is a formula to give us the roots, but as a byproduct, it also gives us h. So it's very handy. The quadratic formula gives us something else as well. It allows us to figure out whether our roots are going to be two equal distinct roots, two real distinct roots, two real equal roots, or complex conjugates. And to do that, let me write it up here again, minus b over 2a plus or minus square root of b squared minus 4ac all over 2a. Okay, the type of roots that you get is totally determined by this term that's under the square root sign. You don't need the square root sign, all you need is a term underneath it. It has a name, it's called the discriminant. And it's b squared minus 4ac. Right. And here are the types of roots that you can have. Two real distinct roots, that's where your parabola crossed in two separate distinct places across the x-axis. You can have two real equal roots. That's where the parabola comes down and just touches the x-axis in one point, or if it's a downgoing parabola, it just comes up to the x-axis and hits it in one point. And the third type of roots are complex conjugates. Okay, looking at b squared minus 4ac. If b squared minus 4ac is less than 0, you're going to get complex conjugate roots. You can see that because if b squared minus 4ac is negative, you'll be taking the square root of a negative number. This is the this will be imaginary number. So if b squared minus 4ac is less than 0, then you're going to get roots that are complex conjugates. Right. If b squared minus 4ac equals 0, then the roots are going to be equal. Well, why is that? Well, if b squared minus 4ac is 0, then this whole last term is 0. So you would have minus b over 2a plus 0 and minus 0. Well, that means they're going to be the same number. All right? And if you remember from the graph, I'll just try to do it here quickly and I'll tell you about it again. If we have the case of two equal real roots, the parabola comes down and either just touches it at its lowest point, or it will come up here and just hit. So the two roots are right on top of each other right here, and also this is the value of h. It's the value of the vertex, because you see that's either the lowest or the highest point on the parabola. So when b squared minus 4ac equals 0, then you have two real equal roots. They're both the roots are equal to minus b over 2a. H is also equal to minus b over 2a. And in the third case, obviously we have only one case left. We have b squared minus 4ac is greater than 0. In that case, the square root, taking the square root of a positive number, you will get a number divided by 2a, and then now I want to show you graphically what this means. Let me just try to say it algebraically. You will have minus b over 2a plus a number and minus b over 2a minus a number. And this will give us another piece of insight into the these quadratic equations, and will help us to solve things very easily. Okay, I'm looking at this. And let's give some numbers to it. Let's say x is 25, and I'm going to work all this part out here and say this turns into 10. Right? That means x1 is going to be 35. It's really just, I'm going to write it like this, 25 plus 10, and x2 is 25 minus 10, that's 15. From what I told you before, this minus b over 2a is h, so this term is the h. And here's x1 at 35 and x2 at 15. Now I'm going to draw the graph for this a little bit. I'm just going to mark on it. So here will be x1 sitting up here at 35, x2 is at 15, and here's the h. Okay, where's h? It's right in the middle between the two roots. The h was the 25, and to go this direction, plus 10 gave me one of the roots, and going in this direction, which was minus 10 off of the h, gave me the other root. Right, so you see there's all kinds of symmetries and all kinds of little things in here. Of course, they're just, the benefit of them is that they allow us to solve the problems easier, and they also allow us to develop some insight into these quadratic functions, the quadratic function, also the quadratic equations. So now I'm going to translate this into some symmetry. You remember from first chapter about a symmetric function. Symmetric function is, even function is symmetric about the y-axis. So if this really was a parabola, which is a pretty poor representation of a parabola, then this is an even function because what's over here is the same as what's over there. And you have a line of symmetry right down the middle of the parabola. Now what happens if I move that parabola? I'll move it, say, I'll move it over to here. Okay, it's no longer symmetric about the y-axis, but it still has symmetry about itself. It's symmetric right about a line going down through the vertex. Right? Okay, so if this was the h value, here's your h, then these two are equal and opposite from it. So here would be your x1 and your x2. If you have the quadratic function, you get all these right away. The one I did before, x was equal to 25 plus or minus 10. So if you have these values, you can, 25 was the h, adding 10 gave me 35 for one of the roots, and over here 15 for the other root. On the other hand, what if you only know x1 and x2? You only know the two roots. Then you can find h by averaging them. And that's what several of the homework problems are about. Taking the two roots, x1 and x2, and averaging their values and getting x. So if you know the two roots and you average them, you get h. To find k, you have to put h back in the original equation. So this has been a whole lot of words here. I've tried to kind of map out the whole thing with quadratic functions in these two lectures, and now the next one I'll do some samples, and with these samples you'll get more of a feel for how this works.